This is right. Let's get started. Welcome everyone to a new seminar of the G5 Commission of the IAU. And welcome Daniela Korkakova, who will introduce the speakers today in the talk.
So welcome and welcome Marina. Marina studied at Novosibirsk State University. First she focused on fluid mechanics during her bachelor thesis. But later she focused on quantum electronics, which is the current field of interest for her. She worked in laser physics and especially in broadening of spectral lines. And also she worked on the problems with lunar magnetic anomalies. Now she is a senior researcher at the Institute of Laser Physics in Novosibirsk. So, Marina, please, yeah. Can you say us or introduce you new method about study of exoplanet?
At first, thank you very much, dear organizers, for the possibility to present for dear colleagues our work. At first, I'd prefer to constrain the field of my last scientific interest. It's interpretation of transit absorption of hot exoplanets and numerical modeling of upper exoplanetary atmospheric layers. So by some work on spectra push my colleague and mine to the idea of this method. At first, why this topic is so important? Of course, a magnetic field have a crucial effect on the structure and the size of plasmaspheres, and the accurate interpretation of transit absorptions is impossible without the knowledge about whether the magnetic field in exoplanets or not. Also, the second reason why this is quite interesting topic is the dynamo theory, because in the case of our solar system, we have just a couple or just a little more, just a few planets which have a magnetic field. However, for the improvement of dynamo theory, we have a need in a more wide set of planets with magnetic fields. Also, the presence of magnetic field could be some kind of biomarker. However, the biomarkers is very huge. It's a huge topic, and it's impossible to use it like a pre-talk for this speech. By the way, there is the atomic alignment method. It's of course not the only one. Widely known method of estimation of magnetic field of exoplanets is observing of radio emission. However, right now there is the absence of observed manifestation of radio emission from exoplanets, and this is the reason why we started to find something else. Let's start with some basic basis of formation of absorption lines in exoplanets. Maybe it's quite accessible. Sorry. Oh, wow. Do you see this slides or not?
We see them
Now,
perfectly.
See them
Yeah,
well.
we see them.
is it okay? Well, right now there is the slide, the formation of absorption lines.
Yes.
Is it okay? Great.
Yes.
So, when we talk about transit exoplanets, it's quite a simple story. When exoplanets pass through the stellar disk, we can see some absorption lines, which can say us about the content and some basic properties of its atmosphere. For example, the most popular planet, HD 20940. You can know this planet like a series. It's very popular, and this is the first planet which primary. This is the first planet, and its atmosphere, which atmosphere occurs mostly hydrogen, and it was seen by observation in Lyman alpha line through this through its it passed through the stellar disk. However, right now we know that this is not the only exoplanets which has atmosphere. Also, among them is, for example, KL9b, which atmosphere can contain oxygen, ferrum and its ions, and some heavy elements. Especially hot exoplanets have quite rich content. It's not only KL9b and also WASP 121, KL20, and it's the rich content of the atmospheres of these exoplanets gave the possibility to explore its atmosphere, its dynamic, and another properties more accurate. For example, between their absorption lines of this exoplanet are multiplet or triplet ones, and these lines is the object of a particular interest according to this topic. Our story started with the interpretation of transit absorption of hot Jupiter HD 189. This exoplanet is quite interesting because its peculiar absorption properties. For example, the Lyman alpha observation of this exoplanet were done 3 times. However, just the one time was successful. The reason of this variability could be in high stellar activity of its host star. However, the atmosphere of this exoplanet contain not just hydrogen, also the helium too, and this was proved by the observation in metastable helium line. This line is maybe one of the interests because this line made by helium, which is the most abundant after hydrogen elements in the university. And right now, there are dozens of observation of transit absorptions in this line. So this line was seen not just in case of hot exoplanets, also during the transit of exoplanets of some colder planets, and quite good instrument to probe the atmospheres of exoplanets. Also, its interesting properties, but it isn't absorbed too intensively as, for example, Lyman alpha line, and could be seen by ground-based telescope. But it's our happiness if this line is triplet, and it's very important according to our topic. So there was two attempts to observe this line during the transit of HD 189, and it's quite different properties, like height and height of two parts of this triplet is quite different from one observation to another. Stop just for a second on this peculiarity of this line. It's triplet, so we have to see three lines. However, there is just two parts. It's because of two of these lines is too close to each other, and we can separate it. So it's just a sum of two of lines of this triplet. So turn back to this effect and its story. We noticed that normal depth distribution, I meant the 2g+1 ratio between this height of these parts is broken sometimes, and for the case of this exoplanet. Let's stop for a second on this point. Why 1/8? Why it's normal distribution between the heights of these triplet lines? This is because all levels have its angular momentum, and it's just a simple arithmetic based on simple quantum mechanics. Every angular moment has its own projections, and the number of projections equal to 2g+1. For example, in the case of angular momentum equal to 2, we will have the projection as a number of projection 5. 1 give us 3 projections, and 0 1 projection. Okay, and the 0 g equal to 0 gave us the blue part of this helium triplet. So these two parts, which have the angular momentum 2 and 1, by summarizing, give us 8/9. So in the case of usual 2g+1 distribution, we will have the distribution between the heights of blue and red parts of triplet helium absorption lines equal to 1/8. So it's the normal distribution according to the number of projections of angular momentum. However, real observation don't obey 2G+1 distribution, and it was observed in the set of exoplanets. It's not a full set. However, it's quite evident that we could have some declination from this rule, and this peculiarity led us to think about the reason of this effect. So the atomic alignment effect is widely known in quantum mechanics. For example, it was applied in the work about quantum clocks, also to explain some effects in space media. It's a work of Yan and Lazaryan and Klopchich. And this is quite popular effect in some scientific fields. This effect consists in a redistribution of population of sublevels of fine structure due to some directed force in the case of exoplanets, and of what exoplanets do. It's directed photon flux. And in the case of, for example, isotropic radiation, we will have the normal distribution. However, as a lack of photons, of some polarization, and also the different probabilities of transition between sublevels, as you can see on the lower picture, give us the situation when the isotropic distribution could be broken, and for the lower layer of this system, also the redistribution of population of level will give the redistribution of upper sublevels, and we could be see this like as the changing of heights of absorption lines. So this alignment effect could be traced by the changing of heights of triplet lines. I decided not to float this presentation by formulas. However, if you have a question about the mathematical aspect of this effect, it's my pleasure to explain or clear some moments, but I prefer to open the manuscript for this purpose. So we created the numerical model of this effect and made some calculations to get some particular estimations on the concrete values of of angular momentum. However, where is the magnetic field, and what its effect on this population and its redistribution? The matter is the magnetic field break this effect, and in the case of the presence of magnetic field, we will have the situation when 2G+1 distribution will go back because of the rotation of quantum axis. So this effect based on atomic alignment in the case of observational quality which we have right now, it's the method aimed to the make it clear, has this exoplanet magnetic field or not. However, in the case of higher quality of observation, we can obtain the information about the direction and the magnitude of magnetic field. Here is some concrete conditions for this effect to appear. At first, it's anisotropic force, which in our case is anisotropic radiation. And in the case of exoplanets and hot exoplanets, like K9b, for example, this condition is fulfilled in every case. Also, we have to have something to align. So the angular momentum of a lower layer should to be more than the half. Small conditions, so not to break this anisotropy of lower layer, and high rate of pumping or transitions between lower and upper layers. Also, in this work, we consider the flat stellar spectrum because of make some ascent on the metastable helium line and its interpretation. And here you can see the link on GitHub repository, and in this repository, all lines which are sensitive to alignment effect is collected. It's quite a big amount of lines. And the interest of this method is the possibility to explore it on the data which we have to date. There is a lot of absorption lines, and between them are some triplet lines, and it's a good case to explore the magnetic field of exoplanets right now. And we did some calculation on this topic. Here is presented here some calculations, and its comparison with observations is presented. And in the case of HD 189, there is a lack of quality of observation, of course. Maybe this blue part could be explained by contamination of by gear coronal emission, for example. However, the case of WASP 69b is the best one. It's observation of high quality, and on this case, can make it clear how the presence or absence the magnetic field can affect the absorption. For example, in this case, we can see that it's more probable for this exoplanet to have magnetic field than not, because of in the case of the presence of magnetic field, we have the best coincidence with observation than without it. The same work we did for the observation of Kelt-9b in ferrum ion line. And here is the same situation that in the case of the presence of magnetic field, we have the best coincidence with observation than without it. So we can propose that it's possible to constrain the magnetic field and its magnitude and direction in the case of increasing of quality of observation. And the particular interest of this method, which what it could be used right now for analysis of transit absorption to date. Thank you for attention. I would be glad to answer your questions.
Thank you kindly, Marina. And we do have plenty of time for questions. Let me just expand the screen so that I can see everyone here.
Sorry, which slide?
I'm just expanding the screen so I can see the audience. So yeah, we could take time for questions, and rather than shout them out, if you could just use that feature where you click the react button and raise your hand.
Do you mean the 15 yes? These slides?
I'm just referring to the audience here, how they would ask questions by using the Zoom feature where you raise your hand. Yes, thank you, Carlos.
One question that comes to mind: this line, this helium line that you mentioned, is fairly high excitation, right? How is that excited in this?
Yeah, I see. Really, this line has a very big threshold between the ground level and the level from which absorption occurs, and it was shown in some works, and some calculations prove this that the basic effect which populates this level is a recombination of helium ions with electrons, and this is it's most probable that it's the basic effect of population of this level.
I think, if I remember correctly, this line was pretty popular as an indicator of activity in late type stars, so chromospheres, magnetic fields.
In the case of solar atmosphere, stellar atmospheres,
yes.
To be honest, I have no enough expertise to prove this. However, in the case of atmospheric exoplanet, exoplanetary atmospheres, sorry, it's maybe the most popular line because of a huge amount of observations. It's dozens of observations. It's quite popular in the case of exoplanetary atmosphere.
Thank
you.
Katya, did I see a question from you as well? Go ahead.
Yeah, that's just going back to this point of Carlos, right? Because the stellar magnetic fields also produces, like via Zeeman broadening, changes the spectra, right? Do you see anything that is related to the stellar magnetic fields? Do you expect, for example, in the oxygen triplet that you showed, do you expect to see something or not at all? It's not connected at all.
It's a very interesting topic to separate this effect in the atmospheres of exoplanets from Zeeman effect, which could be quite important to constrain the magnetic field of stars. In the case of this is quite different cases, because in the case of exoplanets, we can't suggest very big magnetic field, crucially more than, for example, 1 Gauss and this field um, can give a very big Zeeman splitting, more than Doppler broadening of absorption lines of atmospheres. So it seems impossible to explore the Zeeman effect to constrain the magnetic field of exoplanets due to this reason. The broadening of absorption lines in atmospheres of exoplanets is bigger than Zeeman splitting for predicted magnetic field. Have I answered or
Yes.
not?
Thank you. Thank you.
Thank you too.
Other questions for Marina? I'll ask one. Uh, is there any solar system analog to this effect? I'm thinking, you know, magnetic field of Jupiter or Saturn, where you see a deviation in the distribution of states through the magnetic field.
Right now there is no works of this kind. It could be maybe prominent. I've searched the works on the absorption properties, for example, mercury. However, I had no succeed in my searches. Maybe it's possible. However, I would be glad to find something on this topic, but right now I have no material.
Yeah, I'm sorry that, as the solar system atmosphere person here, I can't point you to the right direction. But thanks for taking the question anyhow. Simon.
Yeah, more of a comment than a question, partly in response to Carlos's question and yours. And that's a really nice talk, Marina. Thank you. Helium-1 is one of my favorite atoms. I study hot helium stars, and neutral helium absorption has been my go-to for a very long time. And this is a really nice use of the triplet structure of that 10830 line. It's really interesting. The absorptions are always from the lower level to the upper level, and the lower level of 10830 is actually the second. It's the first, or the lowest lying excited level above the resonance line. So if you're going to see any absorption, you're going to see it in 10830. But you do have to have a warm medium to do that, and the fact that you've got hot Jupiters is I think crucial in this case, and you're not going to see it in. I suspect you wouldn't see it in a solar system planet unless you had an atom that had a neutral with a much lower lying level. Again, iron 2 is you're going to see in a warm place, so you're not going to see it in a cold planet. And I count Jupiter as a cold planet in this context, I suppose. So yeah, those are just my observations to sort of contribution to the conversation rather than a question. And I look forward to seeing more of this. Actually, I was also interested in the use of the magnetic field to break the canonical LS coupling ratios, and we've been looking at magnetic fields in hot stars, and again using helium-1 and helium-2 lines there for the same purpose. But yeah, happy to talk about it some other time if you're interested. So. Thank you.
Thank you too.
Thanks, Simon. Other questions or comments? So I'll kind of reply to Simon's comment then, for the solar system, you're absolutely right that there's nothing hot enough. But I wonder if even a hot Jupiter is hot enough. Marina's view that this is probably a recombination line is I think accurate, with the ground state being that 584 helium line, so deep into the EUV, you need, what, 15 or 20 EV to get to the excited state where you can absorb 10830. And I used that as the basis for looking for this absorption with a solar telescope during the transits of Mercury. Mercury has a known helium exosphere, and if you had the solar wind charge exchanging with Mercury's surface, alpha particles in the solar wind bumping into the surface, being ejected as neutrals. If that was the primary supply of Mercury's exosphere, then they should be in excited states. It's analogous to the recombination where it's non-LTE, and because you've taken something that had a lot of energy and neutralized it, you could imagine getting things in that excited state. And the lifetime there in the solar system is weeks. So once you're in that metastable state, it's very stable and you can resonantly scatter. If the column densities of Mercury's exosphere from spacecrafts are correct, we would have seen absorption if it was charge exchange of the solar wind with the surface, and we did not see it. So there's some other mechanism producing it at Mercury, and we did learn that much from the experiment of it can't be this mechanism generating Mercury's helium exosphere. But yeah, it's very much a space physics question of how to get the recombination in helium to produce it, and I think not a temperature based thing just on being hot exoplanets. It's nice that we have some people that have thought a lot about helium and about this line in particular in the audience. Other questions or comments for Marina? Not seeing any. I think we should thank her again, please.
Thank you very much for application.
Thank
Thanks,
you,
Marina.
Marina.
Really enjoyed your talk.